Maths educational video, parametric surfaces. In this video, we are going to learn another way of representing a surface using what we call parametric equations. So far, our definition of a surface is that it is a graph of a function of two variables defined explicitly in this form, z equals to a function of x and y. What we're going to do now is to use a vector value function to represent a surface. The component functions are assumed to have continuous partial derivatives. Since we have two variables u and v, we expect the domain to be a subset of the two-dimensional space. A surface defined this way is called a parametric surface. Before we look at the geometry of the new representation, let's do a comparison between parametric surfaces and space curves, since they look alike. For the case of a space curve, we have a vector value function involving one parameter or unknown, little t. But when it comes to parametric surfaces, it's also a vector value function, but we have two parameters. So we can think of parametric surfaces as two variable analog of space curves. Now the geometry. The reason why we have a surface is because when we take any point uv in its domain, which I label as D, we get a vector R, which represents a point, because R is a position vector. So when u and v change, so does this point. So collectively, all these points will constitute a surface in a three-dimensional space. Obviously, we want to know when a surface is defined explicitly in the Cartesian form, whether we can represent it using parametric equations. It turns out that that can be done very easily by applying the following trick. All we have to do is to let x be equal to u, the first parameter, let y be equal to v. As a result, z would have to be g of uv. That's because z is g of xy, and xy are in turn defined to be uv respectively. So this is an important result. Any surface defined this way can be represented by this vector value function. We will find this useful later. A quick example, we are asked to show that these parametric equations represent a sphere. So in this case, alpha, beta are the two parameters. We recall the equation of a sphere in Cartesian form. X squared plus y squared plus z squared equals to r squared. R is the radius. This is a sphere centered at the origin. So our strategy is to work out the left-hand side by plugging in the three parametric equations, and to show that the result is r squared. Obviously, the presence of sine and cosine tells us we must be prepared to use this famous identity, cos squared plus sine squared equals to 1. With some simplification, you can get r squared quite easily. It's natural to talk about tangent plane now that we have a surface. We have done this before in Cartesian form, but now that we have parametric equations, we need a new set of procedure to do this. Before we look at how to find the tangent plane, let's define two important vectors. Let R be the parametric representation. We define two vectors R subscript U and R subscript V. These are obtained by partially differentiating the component functions. Ru obviously will be to differentiate these three component functions x, y, z with respect to u. Same for Rv, this time with respect to v. It turns out that the cross product of these two guys will give us a normal vector to the tangent plane. A quick revision on cross product, since we need to compute this quantity. Cross product of two vectors is itself a vector. Let's look at how to get the coefficients of the three vectors I, j, k. They are all determinants. Let's quickly recall the definition of a determinant. The determinant of a matrix AB, the first row, CD, the second, is given by this quantity AD minus BC. A times D minus B times C. This is called the determinant of the matrix. And the matrices itself are derived from the original vectors in an interesting way. The coefficient of I is obtained by blocking the first row, which is AP. If you block AP, you get BQCR, which is what you see over here. For the second coefficient, note that it's minus, and the determinant of a matrix obtained by blocking the second row. You block out BQ, so you get APCR. And as expected for the third, you will block out the last row, leaving you APBQ. So this is how we compute cross products. You must have learned other methods. They'll all be acceptable. But at least this is one of the ways to do it. We're now ready to find tangent plane. We recall what we need to find tangent planes are two things. One is the point, a point on the plane. In this case, obviously, the point of tangency we are given. And another quantity we need is the normal vector, which we have found U times RV. With these two at our disposal, the equation of the plane can be written down easily. We end the video with a numerical example on tangent planes. So here we have a parametric surface defined by these three equations. And we ask to find the equation of the plane at the point where U and V are both equal to 1. So we begin by finding the normal vector. We first find RU and RV by partially differentiating the component functions with respect to U for RU and V for RV. And we take the cross product using the method I've just demonstrated. And since you are given UV both equal to 1, we plug it into the normal vector to get a numerical vector. And this we know is a normal vector to the plane we are finding. So we have the normal vector, we have the point of tangency. The vector equation of the plane can be written down. But what the question wants is Cartesian equation in terms of x, y, and z. So we'll replace RB with x, y, z and work out the Cartesian equation as required.